Okay. So then we're going to go over this process and basically feel free to ask questions at any time. I'm also going to ask lots of questions to the group during this. You can even leave more feedback. Okay. So for example, a lot about this process is figuring out this mythical, magical thing called being productive and how can we actually do this. I tend to really think about this pretty often as trying to find ways so that we don't end up wasting time. And this time wasting time, as we'll get to, we're trying to really line this up with like writing claims for a paper, is like we want to, if in a perfect world, we perfectly define the claims together for some project today. We only do experiments related to those claims exactly and no mistakes. That we didn't waste time. But usually it's sort of like we weren't totally clear on what the claims were at the beginning of the paper. So we ran experiments for a week and it was like, oh shoot, that wasn't quite the claim we were trying to go for, or something like that. Or I don't know, something was forgotten and something wasn't plotted. This happens really frequently. So the earlier we kind of get to this process, faster we can start with that. So this is sort of understanding what this being productive means in a couple of different ways. Okay, so does being productive mean burning as many GPUs as possible? How many people think that's a fantastic way to start being productive? No? Okay, we've got a couple of hands up. Great, so you can leave. No, I'm just joking. Uh, no. Um, I mean, of course, we've got compute and we do want to use it, but we'd still want to use it efficiently for those experiments that'll matter most. So I'm basically here to say, in this, how can we make the best use of all the resources that you've got? That was fast. So the idea is to really, we want to create as much evidence as possible to support the strongest, most impactful claims that we think we can make progress on for some research. So we're going to talk a lot about what does it mean to come up with impactful claims and what does it mean to back up that with strong evidence and build on those two things. So this is tricky because the last part is we also don't want to do any more than this. Like how many people have run some experiments, but they don't end up going into the project or the paper? Yeah, probably like everything. I'll put two hands up for that because it just happens. It ends up being, well, we thought this was going to be a clear thing or whatever, but it just wasn't quite like perfectly aligned with the claims. And at the very least, I don't know, your supervisor comes up and says, it's great, but it doesn't quite align with the story at this point too. So maybe we stick it in the appendix or something like that. So we kind of, if we can, we'll try to avoid that stuff more. So this is thinking about what we can do to help plan and organize a bit together, ensure some of this fabled productivity. And basically, we'll start with making really clear claims, some plan to make really strong evidence for those claims, not other claims. We'll get to a little bit of details on what we can by going over an example. And the last part, if you've got all of this, is usually some type of time prioritization to adjust these. So if you've got a couple of claims in a paper, eventually you have to run one thing before another. There's usually always one strongest claim in a paper. And that's the thing, you should run experiments for that first. Even if you come up with a laundry list of experiments that like you and your supervisor agree on, there should still be some ordering to them. And they should be ordered by, okay, which one of these is the most awesome claim that we can hope to make? All right, so I'll start this with a little bit of a project in mind. So, Semix, any questions so far? Good. Yeah. Hmm. Ah, 70 hours. That's good. Mhm. Man, I would always say you need to at least spend 15% of your time every week reading papers, whatever that means. So I put time limits on this stuff for me when I was doing these things. At least when I was doing my PhD, basically my morning was reviewing the absolute landslide of data that I generated from all the experiments over the night and fixing my code and starting experiments. And then my afternoon was reading papers, maybe doing some more coding for stuff that wasn't as related to those most immediate deadlines just after. So I guess I would say block off time. I guess maybe I'll get to some of this stuff. I use Reclaim, which literally blocks off time using an AI tool in my calendar. It says like, this is Glenn's focus time. So when the people who use my calendar suddenly block it up, my calendar kind of defends itself in the last bits. It's like, no, Glenn wants at least 4 hours every week, and it'll block up all the rest of the spots in my calendar automatically. And then I'll use that for paper reading, paper writing, things like that. So yeah, I guess that's a different question. I also don't do meetings in the mornings so that I can get this stuff done like this. Although I accidentally, serendipitously, woke up at 5 a.m. this morning because I'm still kind of on South Korea time, I think, and then started making these slides. So things happen. But I would say make a budget. Like you budget for stuff in your house, you should budget. You've got so much time. You need to read some papers, code. Don't spend too much time coding either. That's actually like a sink that you can get into where you think, oh, I just need to run one more experiment. It's like, no, more often I've seen people go read another few papers, come up with an idea to increase the like strength of the claim. And that's better than just trying to make the current claim more clear. Yeah. Okay. Other questions? Yeah. Ah, this often sounds like a case of don't let perfect be the enemy of good here. It's like you've got to budget your time. To make something perfect means that you basically give up everything else. You don't do any other paper reading. You only focus on like doing that one thing perfectly. I guess I'm trying to say you should always start from a problem. You should never just start coding stuff and not know why you're coding those things. And I mean like almost literally like every line of your code should be directly connected to a claim that you've agreed on as the strongest claim to work on. And if it's not that, then we go back to no more than this. You're now doing more than is necessary, and it's possibly a waste of time. Sorry. But I get these things are sometimes hard to figure out, but that's why it's like claims. And we'll talk about evidence and how to support them. And like only if they're in this somewhere connecting these things should they be done. Otherwise, uh, not sure. Maybe there might be a few things you can do for like the enjoyment of learning and figuring what they are, but they may not help like the paper get accepted. And I'm not trying to be like harsh or anything or anybody on here at all either. It's actually because I think like everyone in this room and at Mila is fantastic. And I want to see them do awesome things. And that usually would mean those like, so that means organizing time a little bit better, such that like you can all have way more impact on the world and way more positive impact. Yeah. Okay. Okay. So, shoot. I guess I didn't turn on the animations for this particular slide. Oh well. So where should a project start? Maybe close your eyes and don't look at the bottom. Um, so if we have an idea, should we just go start coding that idea? How many thinks how often have you maybe started with that for a project before? I think I've even done that a couple of times because I'm good at coding and I would rather do that than go and like read papers and come up with a strong claim right now. It even becomes kind of like self-fulfilling. Yeah. Did you have a question? Okay. Sure, no problem. So if it's not to burn GPUs, what should it be? It should basically be to figure out how to make really good, solid information. And this is why we need to start with claims. So I've got a colleague of mine who's another fantastic RL researcher, Eugene here, where he says he goes through his process for filtering out literature is to find a small set of authors and read their stuff almost religiously. Basically, this works because those people are now good signs of consistently producing strong research content all the time. And that's what everyone should basically strive to be. Whether or not it's research, a lot of these rules also apply if you want to do a startup after this or something. They'll still be like milestones you're trying to hit. And you want to be able to hit those milestones and claims and things like that. And other things just aren't on the path to getting that done. So we'll talk about how to understand, kind of make sure we can make some consistent sources of knowledge and move from What I like to think of these days is like the academic process of going to grad school is to move from becoming a consumer of knowledge. You're going to have to become now a really good producer of knowledge. Like you're in this process now, creating what sometimes people think of as a science is this giant pile of rocks. And then when you've done your bit of research, it's like, oh, it's great, it's the stone, you stick it on the pile, and then maybe other people can keep adding stuff onto this pile over time. And that's basically what I want to keep building on over time over that too. You can sort of visualize this creative knowledge. Okay. Does that make sense? Yeah. Uh, he explored for a bit until he could find the few people that seemed to have like consistent information. And then after that, it seems like, yeah, Eugene stopped exploring. I guess you kind of need to make those choices at some point too. Like after claims have been defined for a paper and we've pretty much agreed on them, then we might to potentially avoid some serendipity, maybe kind of refine the project a bit to not explore additional mathematical concepts beyond that for now. Uh, and that's usually where I tell at least all of my students, all right, your paper's done, you've submitted something. Don't think about anything. Just like go and read papers for 2 weeks because you've been like corrupted by being in this non-exploring, only exploit zone for a while. And I need to go get some fresh ideas and pull your head out of the hole it's been in trying to get that work done. Yeah. Uh, I would think so. Like, there's always some trade-off to be made once some projects and some claims are chosen as the things to support. And I think you're trying to getting at the point where, okay, so there's one example where you could see whether or not there's some tools that work in some area of like the machine learning community, but they haven't been applied elsewhere. So you could maybe see if those tools work in this other spot and they might work fantastically. Is that the example you're kind of giving? That's a good way to do research. In fact, basically most of deep reinforcement learning research, that's like I do deep RL, is just that. It's like, oh, cool, this thing is working in supervised learning group. Let's just try and duct tape this around reinforcement learning and see if it works. And it's been very successful. Well, now we kind of don't like it, and we're going back to the kind of whiteboard again and realizing this now doesn't work because it doesn't support continual learning well at all. But that's fine. You got more research you can always keep doing. So I'm not saying that there isn't like there's no bad form of doing research. I'm mostly just saying it's come up with some claims and a plan, even if you want to, yeah, figure out whether or not methods will work well in some other area of the community. Yeah, that's great work. Mhm. Yeah. Uh, Other questions? Can you speak up a little bit over the air conditioner? It could be both. So I'm not sure. You'd have to go ask him. He's only on Blue Sky these days, so you can message him on there if you want. We all know the next slide is going to have a couple of jokes about the uselessness of Twitter, so that'll be good. Uh, okay, so I think we're good here though for now. So we'll start to get into editing. So then basically what we can try and do to the best of our possibility, um, if we're trying to figure out like what knowledge we want to be a producer of knowledge, we basically just like run this little experiment. So, okay, if we did this project, what would be the knowledge that we produce? So just like literally, let's try and visualize the paper at the end. That's what we're going to do. Hopefully by the end of this workshop, even though I've already used up a little bit of time, a half an hour, hopefully we're going to finish 2 papers in this workshop in the last hour. So it's high hopes, but I think it's possible. But basically, we want to be able to visualize it. So if you've got some paper, or at least some idea, let's go through the process of what it would look like. What are the claims for that paper? What would it look like to actually put together the experiments to actually do that paper? Are those experiments even possible? It's like Glenn's claim is that he can move Venus, like, I don't know, a couple 100 kilometers closer to the sun. It's a great claim. All right, is it possible to run experiments to do this right now? No, unfortunately, I'm working on it. It's one of the reasons I really like robotics, but it's probably not something I can test out today. But there may be some point in the future. So I keep track of a whole lot of research ideas where I just know the technology is not ready yet for these as well. Those will be things you can check out later. So that's a little bit what this is about. So we want to be able to visualize a pretty clear final version of the project. That's where we're going to go through basically drafting out two of these today. Best option, if you can, invent a time machine. Also a work in progress, not currently an option. Next best one, try to predict the future the best that you can. And these days that is becoming trickier and trickier. And that's why I've got Eugene's other comment here that I've really liked from a couple of weeks ago, because the single biggest challenge is basically figuring out whether or not the internet, or these days the scientific community, is remaining calibrated about what is the actual normal understanding of how science is working, even though everyone's just kind of wrestling with each other to figure out what is supposed to be the proper output and what actually works. Uh, and let's just say things are not as clear as they used to be. Does that make sense? No. Like when I was doing research, I think there was an order of magnitude less papers published, I don't know, every year during my PhD. There was far less noise, far less things I had to read. And these days it becomes even more difficult to understand what are the things that are actually working and what are the things that some company took the same idea, threw 10 times as much compute at it, and it worked a little bit better. And was that actually useful? Things like that. So it's really hard to figure this type of stuff out these days. And the people that can do this really well, I don't know, those are the people that become professors, because we literally can't run experiments anymore. So we have to work off of just this cloudy, noisy information, from papers, which is not great, with a few exceptions anyway. Okay, so we're going to draft a version of a paper, and we're going to assume like everything in that paper goes according to plan because it's the best we can do. So we might not worry about serendipity too much because it's kind of hard to plan for, although sometimes it helps. All right, but how? So basically, we'll go over the important part is just to be as realistic as possible with coming over this plan and be a little optimistic. Sometimes things do work out. Like if you just look at all the bad stuff that can go wrong, you may not start any project because most of the time things will not work. And maybe 10% of the time things do work after so many experiments. Okay. So any other questions? Sound good? Okay. So where are we? So I want to start with this and then we'll go back to the previous thing. The first thing I want to know, okay, is the idea impactful? So what does this idea improve? So this is like, we're not starting with a mathematical concept. We're basically starting from the beginning of, we have some problem statement and we want to understand, is this actually helpful? So you can have some example of this, but usually you're thinking of something like you want to cure cancer. Great, it's pretty impactful. People will be able to live longer. They can do more science with that extra time. So we'd all be able to have more extra knowledge. But basically, if I take just one example of this, and we can start to understand what does it mean to have a more impactful claim. So let's say, maybe I'm guessing a lot of people are computer scientists in the room. So we could have a problem we want to work on. We want to understand if one number is bigger than another number. We could do this in two ways. We could have idea one. All right, we're going to sit down. We're going to prove that 55 is greater than 34. Does everyone think this is correct? Right. There's not going to be any trick questions here, by the way. Okay. It's a little tired already on Thursday for trick questions. Idea two, prove that x plus 1 is greater than x. Which one of these is going to be more useful and impactful? Two. One is only useful if I happen to be comparing myself from many years ago from someone much older than me, and only in that case. So it's got more assumptions. It only works when you're comparing 34 and 55. And we'll kind of go with this as like we want problems that end up being, in some ways, something that are more general rules that people can apply. Okay, and then the idea to understand what is impactful in more general is like Really, it's go read more papers, go to conferences, see what improvements would help everyone else the most. For example, I was just spent the last week in Korea. A bunch of people are doing robotics. They're all just training millions of dollars on big, giant foundational models. And they're just kind of randomly picking when to stop training these models. So they all really need to figure out when to stop training their models so that they actually work well. So that'll be something that I figured out because I just looked at many papers and 40% of them have this thing where they pull basically a number out of their hat. We will train this model for 300,000 steps. We will run it and just stick with that. I don't know where they get these random numbers from. That's one way to do it. The other one that I also like is what do you need? Like what tool would actually make your research life easier? This is actually the concept that Google uses very often, where it's sort of like, okay, they're tired of trying to write manual algorithms to try and like decompose matrices. If only we had an AI tool that can figure out how to iterate through possible algorithms faster, then that would make their daily job of doing computer science easier. So this is literally that concept of what would actually help you with your research. Most likely, if it helps you, it's fantastic for everyone else around you as well. And then just be like, I found this thing. It works great for me now. Share it. Start using it because you'll have more knowledge and you'll be better at building on it than everyone else around you. But then you also get credit for that. Yeah. Do those two make sense? Any questions about these so far? Yeah. Yeah. Yes, basically. And conferences are becoming even more of echo chambers because that kind of goes back to at least Eugene's comment here of how going to a conference, which is could be a version of some social media or whatever, can look like its own echo chamber. So I mean, you can go to a conference and at least collect the information. I wouldn't make a decision based solely on what one person told me at a conference or something like that. The thing that I often think of to improve on here is like come up with the problem yourself. So by that I mean don't go read papers. So like if you've got a solution they think is a good mathematical solution, don't go read papers first. That's right into the echo chamber. Go with a proposal. It's like work out the math for it, spend like half a day doing this, see what your solution would be from that for that solution, and then go see if there's papers that look like that. This is also really important because if you're starting out on a problem, and if you don't really start working into the details, almost any random paper looks like it's done your idea already, and it actually hasn't. It's rarely true that two ideas are exactly the same, and it just sort of looks like, oh, this looks like the idea I had, but actually they're not using the same method or they're not the same experiments or environments. So you have to at least spend a little bit of time with an idea. But I would still recommend going to conferences. It's mostly because talking to people is helpful. The When you get to talk to a person, you basically get to interact. This might seem weird, with another object in the universe that's a whole nother lifetime and lifetimes of experience that thinks about these problems. And that can give you a lot of unique perspective. So it's sort of like accessing if you could copy yourself and explore your whole life differently and see what you'd end up as a result. So it's a really kind of unique form of exploration. It's the way I think about it. So it might not be go to the conference. Okay, actually, I didn't read many of the papers that were there. I went there to talk to everyone that I haven't got to talk to for the last 6 months to a year to see, like, okay, do you still think the same thing after the stuff that happened last year? Not so much the papers I already read before I went to the conference. Yeah, so that helps. Okay, other questions? I also find to address this one, watching talks is good because talks are usually more broad and they're not so, hey, look, I'm selling my method in 5 minutes because that's all that I'm allowed to have in this program right now for the conference, and you can only say so much. So I'd really recommend watch more talks. You're getting into stuff, so you can watch keynote talks and stuff at plenty of conferences. There's plenty of reading groups that record stuff. And they're usually much more accessible, so you don't need to know as much theory. So in my case, I can watch them while cooking basically every night, so I don't have to pay as much attention. Okay, great. So let's start with an example. So, and this is where we'll actually start editing stuff. So I'm at least going to start with this one, which are all probably somewhat familiar with. So let's come up with this whole process for making convolutional networks. So we're going to go through an example of like how we would write the introduction, like a bit of a template for that, some of the abstract for this. What experiments would we need to do to show that covnets are the thing? Okay, but the problem is we really want to do image processing, right? Image processing is an absolute pain in the neck. I know you might not think about this now, but especially so 20 years ago, I think that was the covnets paper, something like that from Ian LeCun. So the problem is, start with the problem. Is it important? So image processing is very important. How many of you have not trained a deep network, tried to just sit down at your computer and write a program just in Python to try and process an image? Okay, where would you start? Like, okay, so you didn't use deep learning at all to process an image. You didn't use OpenCV either. You just wrote Python and if statements and for loops. Really? I'm sorry. A little bit. How did that go? Okay. We filters. Ah, yeah, same. But did those work well? A little bit. You still had to have a lot of calculus to even start to get to some edge detectors and things like that. But in the end, I bet it was pretty tricky. Like tell the difference between a cat and a dog. They don't have smooth edges, so I'm cheating here. I'm a strong adversary. Well, that's like part of my point is that like image processing, part of the reason it's gone down the machine learning route, it's really hard to figure like what would be the program that actually makes this work. And there are lots of like unique examples where it's really hard to tell the difference between a cat and a dog as well, that even like machine learning methods can't figure out. So there's this challenge of we want to write programs to help us process images, but it's too hard to program them. So this is a really important problem. Also, what was it? So you can figure out who this problem is important to. Sure, it's important to all of us, so we don't have to write programs as much that are complicated. But basically, the most common sensor that we have, like on the planet, as far as I know anyway, is a camera. So there are cameras and images everywhere that we can use. So that means we're developing a possible data processing technique for the most common sensor hardware on the planet. It's most likely very helpful for tons of people and has tons of industry applications. So very important. Not so it's basically I'm trying to important there. It's important outside of our community as well, not just for like me and like two students or something like that. So what can also help is maybe how many people work in that area. Can look into that, so that can sometimes determine importance. I don't know. I guess like I don't necessarily work on like robotic rippers that are only good for picking up a specific type of rice or something like that. It gets very narrow at that point, so it's not providing as much impact for as many people. The last one that kind of comes into this is like you might have a really important problem, but no one's going to understand you. Uh, this might also be like the Jürgen Schmidt-Hubert version of this, where it's sort of like it sounds like an important problem, but you couldn't quite communicate it to connect the things together. So no one really understood what you said anyway to begin with. And then other people might come along and be like, here is it explained a little bit more clear. Here is an example on a data set you currently have in your hospital. Here, it works okay. Pretty a lot easier to understand. So that's the stuff that you should really have in like the first 3 pages of the paper to keep people like understanding why you're doing this. Okay. So we're going to kill with along with this image processing as an example. We talked a bit about why it's important, and we already talked about why it's impactful. What does the idea improve? We can process images better. What can we claim the idea improves? So that's where we're going to get down to some of the details. Stronger claims are always better. And I guess we'll get down to this and talk about stronger claims in a minute. But the challenge is being able to justify them with some evidence or support. So usually a stronger claim revolves around a couple of different things. Sure, this is an okay claim. Ends up being a better claim because this is a more reuseful tool. And then we'll get back to impactful and novel ideas later. Okay, so let's go back. I invited you all to this meeting, and in the description is the link to these slides. So you can go back to this version of a paper that we're going to start editing together now. So this is the draft that I've kept for doing research proposals for the last couple of years. So we'll start with this for Lycom next. So we want to be able to short or write some abstract. So we want to noodle to it internet. I don't know, something like that. So, we oh, tool to cats and dogs. Sure. Probably should actually leave the abstract till the end of the paper because it's usually just a summary. So what we really want to get to is here. Okay. We want to start with these. What is the main problem? How do we solve it? What are the proposed methods? What are the claims? All right, everybody. What's the main problem we're trying to solve for research proposal contents? Anyone want to offer like a sentence to describe what the main problem is? Okay. So that wasn't the problem though. You said you propose a model. So you're already talking about the solution before we talk about what the problem is. So this would be in the area we propose a model to process images and more. But what's the problem? Why do we want that model? Yeah. Sorry, can you say that last part again? Hmm. Okay, yeah, that can be part of a problem. So like, because it's usually a problem is to like avoid manual design. Like it's the problem is we don't want to have to do that design. Like it's hard to do that in some ways, or at least very time consuming, and there's tons of them. Yeah. Other ideas. Yeah. Hmm. Okay. Yes. Okay. But can someone tell me a little bit more, you or anyone? So like, why do we want to process all the images on the internet? So it's sort of like we're kind of assuming that we want to do this, but we have a reason for doing this, I'd hope. We want to be more accurate. So you're saying like you want more data for the data set in order to train the model here. Well, let's assume we don't know that covnets are the answer first. Now we're just coming up with a problem. Yeah. Yeah. Yes. Okay. Thank goodness for that generative model. It's fixing my spelling while I do this and type. Okay. It's true. I think that that's not the problem though. I think this is good for impactful, like the impact. So this is whatever the problem, this means huge impact. Still don't quite have the problem yet though. Stab at it. Sorry, can you say that? not scalable. Okay, let's just say we need to unpack not scalable a bit more though. I think we've all grown way too accustomed to this word just to think that like we want things to scale. Mhm. Yeah, I mean that kind of goes back to the problem before you're mentioning of like having more data and possibly better generalization. So it should generalize as we get more data. Okay. All right. We're getting around a lot of the challenges here, but I think there's maybe a version of this that's a bit more succinct. You want to give it a try? Hmm. Sounds like someone just looked up the covenants paper and checked the first couple of sentences. So I think that's good and that's actually pretty accurate. Okay. But maybe I'll also get at a point because I'm trying to not make this too specific to covenants. So I guess is there a way of coming up with a definition for the problem and we won't use any machine learning terms at all? So like this shouldn't depend on machine learning. This problem just exists in the universe. And we're going to propose like machine learning and covenants as the tool to do that. Yeah. Speak up a little bit more. Good. Yeah. Nice. So this could be I'm going to make up a few numbers here. So let's just say people spend a total of, I don't know, 10 hours a week processing images. What if we can get that down to 5 hours and then come up with a method for being able to do that? So our problem is that image processing is everywhere. There's definitely some tools to do it for covenants, but we're just talking about like generally there's this concept that people are spending a lot of time on this or it's not easy. And if we can save time for people, the problem is that people are basically using a whole bunch of time for this thing we think we can automate, but it currently takes a whole bunch of time for computers to do it or just people to do it. So the problem is really just that image processing is hard. Um, but there's a bit of a connection to like the value of this here. So if you can improve on this, hopefully we can somehow save people time. Mhm. Yes. So this, okay, so cool. This gets into the next step. So this is like higher level how you plan on solving it. So I think, yeah, we had a few comments. We want to process images, but the concept, again, we're not talking mathematically at all yet, technically. So it's just a dog in the top right corner of an image is dog in the bottom right. True. Everyone agrees on this statement, I hope. No one has any really weird dogs. Okay, now we've got like a little bit of something we can build on. We've got a problem, which is we've already shown that it's going to be like impactful and it's a problem. So the problem is being able to process images. It's impactful because supposedly people spend 10 hours a week doing this. And now we've got a concept of a solution. It's like, well, actually, images and some of the stuff in the images, uh, like where it's located in the image, is actually not important. So that means, okay, now how do we come up with a mathematical solution to express this? And maybe some more complicated mathematics to encode it. So now we can get to this part. I guess this, yeah, save everyone 5 hours. We can get to that later. And then, okay, we pose a method to all right, people know what I mean by that. Like now we propose some mathematical method that'll do the thing on the above. Uh, we call it, well, that's something like that. Okay, how we doing? So like questions so far? Does this make some sense? For like the problem statement is usually totally independent of mathematics, like very often. And is usually something that's kind of like a bit more society related. It usually just takes like the first sentence or two of the introduction or something like that. And it's to convince everyone and not just your supervisor or the person who loves your research area, but the people who don't like your research area, that they should get interested in your research area because it's this important. Okay. But any questions? Yeah. Sorry. Hmm. Uh, a bit of yes and no. So like, okay, this is still a proposal that this problem is an interesting problem and that it will be useful. So yeah, like a reviewer seemingly can obviously disagree with this on the very first step of the paper and say like, no, actually, I don't really care about anybody's time. I only actually care about dolphins. And what does your tool do for dolphins? And I bet you there are actually people who will only care about that and they like dolphins more than people. I can kind of understand that. So that is an important part. Like this is, okay, it's an important part. It's not usually a great one because this gets down to a problem in our community that's called taste making, which means like it depends on what your preferences are over mine on whether or not this is important, which is not good. And instead, it should be more abstract and not so personal so that we can say, like, if we can somehow boil this down, just like, all right, my method saves people 6 hours a week and yours only saves them five. So mine's better. Then at least we've got some more equal measurements that we can make. But unfortunately, very often in many different papers and conferences, this isn't structured really well. It's a bit different. I guess I'm like a bit biased for all this stuff, but at least for the reinforcement learning conference, we introduced a cover page, which is you have to write the claims and your impact clearly. So you can't hide this stuff. And it made it much easier to process papers and understand claims and make the reviewing process less biased and less subject to taste making. So sometimes journals are better at this as well. Okay. So it's not perfect. So yeah. Okay. Yes. Underappreciated but important. Um, How do you know that? I'd say that's really difficult to know. It's not easy. One thing I would suggest is go back to, so I highlighted a talk here. Go watch this talk. So this is a nice one. Do any of you know Jason Hartford? Okay, so he gave this nice talk on retrospectives on how to choose research questions, which is a good addition to this. And he basically says you should try and include things that are doing good counterfactual impact. So it's like other people would not have thought of this. And because you discover it earlier, you give an overall huge impact over this and what other people would do instead. So you can maybe think of that, but that still doesn't really answer your question. Sorry, it doesn't say like, so what was that thing and how to feel confident that it will have impact. So that's challenging. You have to have some intuition, maybe some small experiments that you can do really quickly to start to give you a bit of confidence in that intuition that maybe there is something you can try there. And of course, he gives the experiment for GANs, which is not an easy one because that was supposedly thought up in a night and done an experiment that magically worked. This is like 4 acts of serendipity happening at the same time, which rarely occurs in science. So, but it does mean like no one was really working on something like that. And well, now no one really uses GANs anymore, but I won't tell certain people. Um, so yeah, it's a bit of a challenging process. It is, however, how I like to do research. I'm not always a big fan of chasing what is the most popular idea because that's what everyone is working on. So that means like if I'm there and I'm not there, there's no difference to what happens. I want to go where I can actually make a difference that I don't think other people would do stuff. So that's really what's meant by this contrapositive thing. But you still want to, and I think that can work out well, uh, as long as you still have like a good problem statement. You can tell people it's like, okay, this method will still have impact on this important problem. And then just say like, but I've got a really unique idea about how to tackle this still important problem. Yeah. Okay, let's spend a few minutes on claims here. All right. What kind of claims do we want to make? Sorry, doesn't re Oh, good. We can, okay, good. Uh, any other ideas? Mm-hmm. Okay. See if people remember their math. Simpler than SIF features, etc. If anyone happens to remember those, I think they're all totally out of date now. Did you have a question or no, you? Okay, sorry. Okay, cool. No problem. Yeah. Yeah. Just that always seems to be the example for whatever reason. You can do it both ways. I think actually the claim in the paper was radiologists can test 3 times more patients, something like that per day or something like that. Cool. These are all good claims. Hmm. Hmm. It's just a value isn't necessarily a claim. Because like so the value, I feel like this is the value. The fact that we can do this with less domain knowledge. But the claim is that I don't know, it's a tricky differentiation here. I guess the value usually corresponds back to the original problem statement some more, and the claims have more to do with the actual technical method and how you're going to show that you're going to provide evidence to support that the technical method is the thing that helps with that original problem statement. So there's a bit of like a sandwich going on here. So if we've got our problem statement, we'll come up with our method that should be able to develop well in that problem statement. And then we're going to really, it should really go the other way. So then we'd have the claims we're going to use to support them and then remind people like the supporting those claims like, okay, and now because this doesn't use SIF features and it can process things faster and might generalize better, and we get this value of it saving us more time. So it's kind of like good stuff to put like in the conclusion or like at the end of the introduction. Okay, so let's just say I'm going to skip over the method section for now, but maybe we'll get back to it because everyone probably knows the method section and we can focus on the other content. But yeah, can you speak up a little bit more? Hmm. That can be an example of it. Yeah, overclaiming is often an issue. So maybe since you brought the question up, maybe I'll jump back to this real quick. Uh, Overclaiming. Okay. So there's a challenge of defining like a very clear claim that doesn't provide any sort of overclaiming, because you might have said, like for example, one of the claims that I think we wrote up there is that now you don't need to provide as much domain knowledge. That might not be true for all cases. Like if you want to make that claim, like what kind of evidence would we need to support that claim and make it so that you don't need to provide, like it's less domain knowledge for any task, any data set? Does this mean that we now need to run an experiment with every single image data set that exists and every future data set? So that would be technically, if I was to go back to this one, I would say this, which is kind of in this value proposition, this would be overclaiming. It's a hope, but I would still like processing images less than domain knowledge for radiology, assuming we do experiments with the radiology data sets and cats versus dogs. And then I will let the reader themselves interpret whether or not they want to do the internal mental computation that it extends to other data sets. I'm hinting that they should do that, but saying that is overclaiming. Does that make sense? Just questions? I feel like this is not that simple. So yes, I would not overclaim, but I would put in the future work. I was like, people should try this on other data sets to show that it also can work well there too. So still not technically overclaiming. You should put it, you're quantifying the amount of this claiming in the limitations and future work section to say like, technically we think this should work. We just have not had the time to do this. Yeah. Yes. Yeah. I would, yes. So this is, yeah, part of the idea is to get here. And it's like, okay, so are we all kind of convinced that covenants sound like a good idea? Is it worth maybe trying to run some experiments now? Oh, okay. Okay, it's a good point. I don't have any images or something like that right here, right now, but what is it going to need? We will use deep networks. They do exist at the time. So this is probably like background section on deep networks to explain some of the mathematics. And then we're going to say, create a small uniform filter that will image works well with large matrices. I'm still not really giving details about how a COVNet works, but usually we start to come up with a method now, or we had a little bit of a method in mind. So like now it's, to be honest, now that we have these things up here and we know we have this dog in the top right corner, this means like, okay, now we can go and find a whiteboard and start to work out the mathematics on how we might try and solve this and maybe spend like an hour or two trying to work out a really, really rough idea for it at this point. But I'm basically saying you kind of want to start out with these parts to avoid manual design. So like the problem statement, why it's important, how what it'll actually help with, and then get into the method here for like, okay, now we have a method and the concept of a method. And then usually, at least for the way I like to write papers, is I'd start with the concept and then I'd actually give a little bit of structure and mathematics about how it would work. But then like the actual details are in the method section. Does that help? Hmm. Yes. Yeah. Well, here it's yeah, I guess we're already refining our search space and possible methods we can explore. It's at least we've agreed that this seems like a conceptual good thing that before CovNets didn't exist. And now once we get to this point, I think we could figure out how to mathematically do this. But maybe the important part I'm trying to make is like, okay, now we think this is promising. Before we didn't have a problem statement, potentially, and we didn't have a way to solve it. We just maybe had an idea for covenants. And if we just have the idea for covenants, it's not sure like what kind of like symmetries or what kind of benefit this thing actually provides. So it's better to kind of go into it with a conceptual idea of what this how this thing is going to do better at the problem. So this also, like I would say, like you've only got so much time to whiteboard math, unfortunately. So you even kind of want to have a few of these steps beforehand to make sure you whiteboard the math that looks like it's more likely to solve the problem. And then you might get to like the method section and the code. So it's to even help before you start drafting mathematical ideas, try to refine those a little bit before you even explore those as well. Hmm, the most revisited? I find that the claims are the most revisited ones, depending on how the experiments work. So uh, maybe one part that I'm trying to point out here is that I often find that it's a bit of it's the wrong direction to go, where it's like come up with a mathematical idea, start like writing up code and coming up with experiments for it, and then try to come up with a problem it solves and a reason why it solves it. It's a lot of work and it's very confusing to do it that way. And I find that people and like the research doesn't always aim for like a really high bar and a lot of impact when it goes that way. So instead, start out with like the problem statement and the impact and conceptual reasons why it might succeed. And then always keep that really awesome problem statement and those claims in mind, like the ones you definitely want to be able to make. And then if you do that, you always end up nudging the research to being better impact. So you kind of always end up with a better result on average or in expectation than to sort of like, I'm going to start coding something today because I got an idea and it's not totally clear what this idea is good for. So like even when like Shannon was trying to sit down and come up with like entropy and stuff is sort of like it bothers I suppose it bothered them at the time. It's like I think there's a connection here between like energy or sorry, I guess like information and being able to process things and noise and entropy and trying to figure that out. So there's the problem is like, okay, if you could link these things together, I suppose you could probably see a bunch of ways you could use that tool. So it's like if they keep those kind of problem statements in mind for like why this ends up being useful. I'm at least hoping in many cases that the reason why you're running experiments is not just because like supervisor told me to, I have no other choice. Don't tell them I said that. Um, something like that. Yeah. Does that help? Or, okay, great. All right. So then we can, like I said, I'm going to skip over the method section, the related work. Uh, maybe at least the part that I'll comment on the related work is the related work. Okay, supposedly its job is to help explain related papers. I'm going to say that's a lie. I found that the best use of the related work is to explain why your proposed idea is better than the last previous methods. So it's not just saying like MLPs are great, yada yada yada, but Cov, Netsk, and Pro. Assess data with some invariances. So like at the end of that paragraph for when you're talking about MLPs or deep learning, it should end with a sentence saying like, okay, but our method is uniquely different in this very clear way than this whole group of prior work. Even though you explained it, really the whole point of related work section is to say like why your thing is uniquely different. So you can head off all those complaints from reviewers saying, ah, this just still looks like deep learning, who cares? Something like that. And then for me, I guess the thing I end up liking to use is we can go over to Scholar, uh, find some paper on a perceptron, sure, add that to paper pile. And this is how I would normally do this in a paper. Go back to this project. Great, dot, 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 include. Oh, this plugin doesn't always work fantastically. What is a perceptron? Done. All right, I've cited the perceptron paper. I've finished my related work section already, sort of. And then, I don't know, MLPs is probably some image processing work. So I'm just saying like these would be paragraphs in the related work section. Maybe something on convolutional networks that might be the actual details. So basically cite some papers. I highly recommend usually finding some tool that's kind of like PaperPile that helps you cite things really fast. And I would always draft these papers in like this process, do this in like Google Drive. Or I like Notion a bit lately because you can at least do math a little bit cleaner and you can copy and paste that right into Overleaf after. Don't write drafts in Overleaf. LaTeX is slow and crappy and it's going to slow down your thought process when you go to do things. Sorry, can you speak up a bit more? Like, do I know if it has one? I don't think it has one. I just tried looking one up this morning, but I only spent 10 minutes doing that to see whether or not I could try using Notion today, and it didn't seem to have anything like that. It's one of its current limitations that bugs me quite a bit. I did find though that at least Overleaf has a paper pile plugin. So when you add stuff for Overleaf, it can group it all together into one BibTeX file and update that file inside of Overleaf. So I might give that a try next week, but I'm not entirely sure how well it works because you'd still have to at least type that stuff into Overleaf, like the string that defines the paper for site. So almost. So this is pretty fast, or at least to make me process stuff. Yeah. Can you speak up a bit more? Yeah, I haven't used Zotero in a while. I got fixated on PaperPile just because it also has a really good app on my phone. So when I download a paper, I can go read it on my phone when I'm on the bus on the way home later. Is it better? Okay. Okay. It was garbage the last time I tried, but that was about 3 or 4 years ago. Okay. 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 Nice. Yeah, maybe we'll give that one a try. Yeah. Okay, but yeah, using some of these tools is good. The part you might also get to next, this is possibly a bit more specific to my lab, but I'm like, does your research project need a robot arm? Because if so, I need to order one and that takes 4 months. But usually you need to define like what resources do you need, how long this is going to take. There's going to be some amount of compute that's available in your lab or whatever, and you need to convince maybe your whole group that you deserve to get to use all the GPUs for 2 weeks. So you should have a really good, impactful idea and a good proposal for like what the main problem is, so you can help convince everyone in your group that your idea is more important to put on the GPUs rather than other people's. So you're already starting in this kind of resource competition process to work out other issues. It's also like maybe you need software. Like you should probably have PaperPile and stuff, but like maybe you need credits for, Azure or being able to query some LLM, something like that. So if you're coming up with a proposal, include some information on this. Because kind of we're getting down into the details now. For now, we have a method, and now it's about we're going to start making evidence and doing experiments. And when you get to that point, um, you basically just want to figure out if there's going to be any hurdles there that you're going to totally get you stuck. So like, what if you wanted to show that covenants works, but GPUs didn't exist yet? Well, then you're just going to kind of go work on something else for a little while and not make a lot of progress until GPUs finally exist. So keep, I guess, some of those in mind for the future. Okay, but I want to get down to this part. All right, so we've got our claims, and I'm going to copy these, at least for now, to help make our life a little bit easier. Maybe I'll just make them really, really small. Well, maybe underline and small. But you can still read them and or remember them. Okay. What evidence or experiments should we use to support these claims? Okay, let's start with this one. So what is the evaluation metric that we're going to use to compare our learning plots or whatever for this compared to prior methods? Has anyone read the covenants paper and remembers what to use as the evaluation metric? Yeah, accuracy. Yeah, let's say we're doing classification in this case. Okay, all right. So we need some, I guess caps lock is on. Great, accuracy. Is everyone okay with using accuracy as a way to compare, let's say, classification models? Okay, I think that's good. Okay, but now what experiments? What experiments are we going to run? And why? These need to directly connect to the claims that we've got in the paper already. Okay, so we're going to connect that back to, I guess, supposedly simpler than this. So we're going to do, if we want to support, I'll give this a number, like this is now 1. I think we can end up doing that claim at some point. Those are sort of the same. Let's call this 3. So cats versus dogs. So then to support 3, train model on cats versus dog data set. Okay, because hopefully that'll end up working well. Okay, is that all the evidence that we need to be able to claim that covenants are a way to train a model and it will be like without needing domain knowledge and it generalizes better than just using MLPs? Or do we need more experiments than this? Okay, what other experiments? Okay. Oh yeah, okay, so that's good. So that's a little bit more. I would usually say like what's prior art or like current uh, state of the art that you want to compare to. So MLP, like if you want to say your stone can actually go on the top of this big giant pile, then it has to be actually on top of the pile. So that's good. So we've got something to compare to. All right. Well then, so what else for experiments? So now we're going to compare MLPs and covenants. Um, always the fun part about being in this room. But okay, we've got to probably at least compare to a few other data sets, right? Otherwise, our claim is only supposedly works with less domain data, but only if you're comparing cats and dogs. It's not a, okay, yeah. So for 3, data sets. Okay. What else? These are all at least sort of supporting 3 kind of so far. Hmm. Okay. Yeah, I think I like this one. I think where this one is more related to 1, right? So can easily, or this one's always going to be hard to quantify, but can more easily perform multi-class Specification, because you can do this without needing SIFT features, and I don't really remember the details for SIFT features and why it was more difficult to do this for more classes. Let's just assume that's correct for now, unless anyone wants to correct me. Yes. At the moment, I'll connect this to one, but to be honest, I think your comment should probably be better addressed by improving the statements on our claims, because this is a bit more like you're saying it's easier to use. It's a tricky claim, though. It's a tricky thing to provide evidence for, somewhat. Like, how would you go about providing evidence to say something is easier than another thing? Okay, a computational efficient I'll agree on. But just because something is computationally efficient does not mean that it's easier to code. You're a fantastic example of that, or at least work. So you could say that covenants are easier. One way that you can show this, and a lot of papers do this, is run experiments across just many data sets. Like, just keep piling data sets on this thing. Didn't have to think, just added another data set, kept going. Not something you'd normally have to do for like SIFT features. I think you'd have to recompute your SIFT features for each data set, probably reanalyze them, which makes them more tricky to use. But for yours, yeah, a nice one would be, so we did include that as a claim, so I guess we can come up here and add to claim for it's more functionally efficient. I think that's correct. So then we can have some support for that, but then we need your experiment. So what kind of experiment would you run for this? Okay, good. Okay. We don't have anything for two yet. What was two? So how are we going to do two? I don't know if this is a specialty of people here because this usually involves some kind of user study, which I'm not a fan. Well, I think they're great. I just don't like filling out ethics paperwork, and I'm not very good at it. Although I've done it a couple of times before. Okay. All right. Yeah, good point. Yeah, I'll be real lazy right now, and I'm just going to put 4, 2. So the compute, it being faster to process means that if some radiologist person is being able to use this for images right now, it'll cut down on whatever that point of their time is waiting around for the image processing task to finish. Okay, I'm gonna stop. I think this is great for now, because we already got lots of stuff. Okay, but the part that I would also really recommend, and I feel like everyone always overestimates this part a little bit, is okay. Literally draw out examples for what these things are going to be and what we expect them to look like. So like if we're doing experiments on cats versus dog data sets. So where is, nope, somewhere I had something open. Well, it seems gone now. Okay, I'm gonna guess this was the proper thing I had open from before. Teaching, like there's basically no excuse to not try to draw out what the paper and the experiment should actually look like and what the plot should look like. Because at least for me, like I can go in here, writing workshop, nothing particularly awesome here. I do happen to at least, okay, everyone in here at least has access to a touch screen, right? You have a phone within the last 10 years that you can draw on. All right, so then you have no excuse to not do this. I do it on my phone right now, but it's new and I don't have a case for it. Really worried about breaking it. But I'm assuming the plot is going to look like this, right? Which one are we doing first? Here to support cats versus dogs. We said, wow, that was crazy. Okay. Accuracy is going to be the y-axis, right? All right, and then we've got epics on there. We're going to want blue is going to obviously be our method because I like blue. And then green is going to be MLP. Okay, that's not good, but I can turn that off. Let me, can I close that particular app from in here? I don't think so. So we just won't mess with that right now. All right, this is our plot, right? This is what we want to put in the paper. Grab this. Obviously try to make it a bit more legible than I just tried to draw on my computer so that people still understand what you're trying to do. All right, so that's plot number one. Draft for it already. We should just replace this with actual real data at some point. Next one. All right, what do we think radiology is going to look like? Basically the same plot, right? Another plot in the paper. I'll just put ACC, epics on the bottom, blue. Let's say for some reason our method is a bit more noisy for radiology. Who knows why? Shoot, no, that's correct for those different colors. MLP, net, up there at the top. Fine, done. Make that a little bit bigger. Go back to the paper. Next plot, fine. All right, let's get to one that's a bit more complicated. How about this? Want to be able to compare baselines for timing. So it's going to be a slightly different plot. What should this one look like? Because this is really the process of why you're looking through this. If we want to visualize the paper and the knowledge that's going to come out of this, we need to look at these experiments and see whether or not they're believable. And we all agree on what the plots should look like and they have to look close enough to those actual things such that they'll support our claims strong enough for it to actually make sense. For this plot, I mean. Shoot. Should be black. So now accuracy. Everyone knows what a wall clock is, right? Cool. So that's sort of like hopefully with training time, I don't know, this would go up really fast, hopefully for um, nets, and then a little bit slower, or maybe a lot slower, who knows? I don't know how to use the delete button on this yet. For an MLP. Sounds okay, right? You can have a couple of different versions of this as well, but this is probably a way of looking at wall clock time. You can also just do some pretty simple tables as well. Like you can also take and just be like for, a batch, and this is time it takes, and this will be like 2 milliseconds for, and then I don't know, 4 milliseconds on average for MLP. Both of these can work okay, depending on what you're actually trying to show. Maybe you can do like this is an average over all of your data sets, because it's kind of hard. Well, it shouldn't be too hard to compare stuff across data sets if you're keeping the same model, but it'll get a bit tricky. But yeah, so now we've got some of these experiments. Snip. And now we've got the data that we agree on. Okay, so just for a second. So do we agree that this is enough evidence to say that the model does have better computational performance? Anything we disagree on? Yes, no? Oh, just stretching? Can you speak up a little bit? Ah, okay. Sorry. So you're saying something with a similar number of like parameters in the model, or ah, okay. So it's kind of getting back to. So I guess we mostly looked at accuracy. Now you're talking a bit more about generalization here, right? Okay. So you, mhm. I do find these ones really tricky though, because you're so if you're changing the model or the data set in some way you hold out data. So like if you're doing this and we got some validation set, this is like our normal way of doing this. But if you mean like this transfers something else that I wasn't really trained on, okay, this kind of goes back to one of the very first comments about understanding whether or not what makes sense currently in the community. Many papers seem to very carefully choose what that thing is that they try to validate on for like transfer to some slightly other, like slightly different data set. And I find that often those choices are very biased. So if you're going to pick that, I guess we'd go back to here and we might have some other claim that we want to come up with. I've totally kind of messed up some of the formatting. But here, not sure if we've got another claim, but it's something I guess we talk more about these days, which is transferability or like zero shot generalization. So now we might want a different experiment to support 5, which is probably something along the line of like some other data set. Maybe we've got like horses uh, versus dogs. And I would at least hope that that model can still classify things that are like dog and not dog and do better than random on this data set, right? Okay. All right. So at least, so now we basically drafted out a pretty good like version why we're working on this work, idea for basically the conceptual way to be able to solve it. I left out some details for how the method actually works from a lack of time. Use the related work to make sure you can say why this new method you've got is actually different and hopefully better than recent work. Remember all the claims that you made at the beginning of the experiment section. Make sure that each experiment that you plan on running here corresponds to those claims. Because very often there are many experiments that run and they don't, like, they're not these experiments to make these plots. They're other ones that don't make quite as much sense with the claims. Okay. Does that make sense? Any questions? Otherwise, I'm going to go back to like the other slides and there's a few like wrap up comments. Good. All right. Uh, okay. So let's go back for a second. Where were we? Yeah, we did that one already. Already did that one. All right. We were on this part. Actually, a great place to go back to just for a bit. So the idea some of the challenging part is to understand like whether or not the idea is impactful. I mean, we talked about quantifying this a bit, at least for CovNets, because CovNets are like image processing is pretty ubiquitous because of the amount of just camera sensors we use. But often there's some better ways to think about this. So when you're coming up with this problem and an idea, like I said, it's really rare that two ideas are exactly the same. So don't really worry about that process too much. You can always find some unique extra claim that you can add on to the list that'll differentiate from you from someone else's work, as long as you're sure the idea you have is good. Yet impact is often measured in size. I'm given this example up here in this corner. because I was talking about that example where often doing research is kind of like you polish this like stone that you're going to put on the big pile of research and it adds some height to it. More often in life, you're better off trying to push the big giant boulders up that hill than you are kind of the small stones. Reviewers are annoying and they don't like small stones. It's hard to see the obvious impact. It's difficult to make claims if they're all really thin. If it's sort of like I have a slight improvement on covnets, but it only ends up working a little bit better in the radiology portion of all those experiments. It's hard to make those claims. So you might as well apparently try to come up with transformers or something instead. Also, a really nice part is if people see you trying to push boulders up the hill, they might help. And they will more often help with those boulders than with other things that are smaller, often because it seems like, okay, that person could probably handle that alone. And there isn't even much for that person to do or learn. So people are often more often known for their larger contributions anyway. So you might as well focus on these, the things that have broader impact, which we'll know because we've got a problem statement, have a slightly more like creative or conceptual solution on how to deal with those problems, given the kind of technology we have now. And it's nice too, if we're going to keep going with this metaphor, and now when you finally push that boulder up on the top of the hill, it adds more to the hill than other stuff. It's also, you can see it from further away. So you kind of get noticed for it a bit more. So you might as well spend your time focusing on these more than, I guess, smaller projects. Go find someone who will work and help push this boulder up you, and you both get more credit doing that larger project than doing like separate individual projects anyway. The next workshop is going to be about how to convince people to help you push those boulders up the hill and not let it fall and crush you at the same time. So that's a slightly different concept. Um, and then after you've worked out this idea and now you've got this like outline that we discussed, now you can go look at stuff at research papers, maybe go to a workshop or a conference because you'll start to tell the difference. And it'll be more clear. It's like, okay, they didn't care about computational efficiency, but we do for an important reason for one of our claims. And it'll just already be obvious about why it's different. Um, is it likely others will have the same idea? Right. So this is why it's kind of good to push those boulders. I mean, I like them often because I find in the research community, people are not so enthusiastic about trying to push boulders up hills. So that means it's less likely I'm going to get scooped on this work as well because it is a good amount of work, but I do believe in its impact and that it'll be really helpful. So yeah, in the community, there's often a little bit of a bias for unexpected things. So it's sort of like no one thought that this algorithm is going to work this way and it ends up working really, really well. And then everyone's going to pay more attention. There's a bit of like a surprise bias in the community when reading papers. Yeah, go ahead. True. Well, there's two real problems with that. So one is it ends up making the claims you can make in the paper really thin because there's so many people doing work in that area that it's just hard to find like a boulder this big. Basically, when you start pushing this up, people are going to start chipping away at chunks of that boulder before you even get to finish the project. So working in really busy areas of research will have that problem. And then by the time you get to the end of this, it might be like, okay, now I've got one of those small rocks, and I'm going to have to spend so much work trying to convince the iClear reviewers that this thing is a boulder instead. And it's just try to start out so you don't end up in that tricky situation. I would say there is even meta research papers these days that show that like the growth of research papers in like the machine learning community is actually stagnating progress. There's now like much more noise than there used to be. And we're all focusing on a bunch of noisy things and overfitting them and don't actually know exactly what the signal is amongst all the noise. Yeah, there's a couple of those. Send me a message after I can share some of those papers. It's actually something that I think like Goyle shared on, I don't know, the Slack channel like 3 years ago or something by now, but there's a couple of other new papers. I tend to stay away from them. And that's why I would go a bit more back to that talk from Jason Hartford, where he's talking about the counterfactual research. So maybe try to be more creative on solutions to these important problems than what everyone else is trying right now. Yeah, best advice I could give for the moment anyway. The challenge with coming up with some of these unexpected contributions, reviewers seem to also be getting lazy or lazier, so they'd have to put more time into understanding the slightly unique look on the problem. So you'll face a bit of a challenge just in writing clarity on how to show that this is easy for them to understand and is also a good way to attack the problem. Yeah, so that's why go look at Jason's talk. He's got some good thoughts on how to come up with this counterfactual stuff. And this is why I would usually say read more papers, think more, do not code 70 hours a week, maybe 40 at most. You're probably better off doing that and reading some papers because you'll find a better looking boulder that's even close to what you're doing right now, but you've already got all the tooling in your code to run that experiment anyway. So you just have to change your method. Okay, I'll say often good to avoid some busy areas of the community. Unless you're absolutely passionate about that, your life will be easier. You'll have more time to think clearly about how to actually solve the problem if you're not in an extremely overcrowded research area. Um, and then, yeah, so talk about how the idea works. So some not so rough ideas. The goal is to basically scope out the feasibility. So if you've got this idea, and they've written out all the project there from before. I think I've got a few more minutes left, so I'm not too late. 5 minutes, okay. The goal is just to basically try to understand if there's going to be any hurdles in coming up with your method. Now that you might have only worked out like a rough idea for it, how to solve it. So you need to figure out, like usually it's like what experiment can you also run in like based on the method section to make sure this whole idea isn't going to basically trip and stumble like right at the starting line. As in, like for example, like if you wanted to do covnets and show they work, well, GPUs don't exist yet. So you're never going to have the compute to show that this is going to be an advantage over SIFT features, at least for a long time. So at least having some experiment beforehand that'll quickly say that there's some life to being able to explore this deeper. And the rest of it is just scaling it up, adding more experiments, adding baselines, etc. And that's a little bit about predicting project length. Check out those like most obvious challenges where I could stumble. Also, occasionally, is the world even ready for this idea? That's a weird way of saying things, but sometimes the community just doesn't care much or doesn't put much thought into like a particular domain or something like that right now. That goes kind of back to the problem statement again. Also, is the tech ready? So Glenn can't go and move the planet Venus like a couple 100 kilometers because he feels like it. That's a future research project. And we went over a lot of this already in the draft, so I can go through these. So make sure that the evidence that you want to generate directly related to all the claims in the paper. Um, one thing to check is too common. Run many experiments and few support the claims. We already talked about that as being like an issue we want to avoid. And few support the stronger claims, so we want to prioritize even those experiments that we wrote in that draft. Like one of those should be done first. I mean, if we care about just the generalization, we should start with that experiment over the time computation ones. And like I said, literally draw out the plots. It only took me a minute. It should only take you like a minute per plot on your phone, and then just screen capture it and drop it in the Google document. To be honest, we did this and when we stopped and took questions, but it only took me, what, 25 minutes in the group here to write one of those project things. And it's good because you're now going to spend the next 4 months working on that project. So I think spending 2 hours drafting up 4 project ideas with a little bit of depth will save you potentially months of work and lead to a much more impactful research. So that's why all this is important. And we got to overclaiming a bit already. And the last part I just wanted to get to, all right, let's play a quick game of claim, no claim. Which one of these are claims? All right. And I got some of these examples from the group here that submitted them. Okay, so uses a hierarchical representation as a solution. Make hierarchy a first-class primitive. Matryoshka representations produce a nested course of fine embedding. Is this a claim? So right hand claim. Left hand, not claim. Your left, my left. I know it'll be right for you. Yeah. So this isn't really a claim. It's not saying that something is better than another thing. So it's sort of a lot of times I see claims or things that are put in as claims or contributions, but they're mostly statements about the method. Okay. Maybe one it's a little clearer. Okay. Proposed algorithm X improves performance on image processing by 14%. Right hand for good claim. Sounds like a claim. Can write an experiment that'll show this is actually true. Okay, good. Oh, you don't think it's a good one? Okay, true. Yeah. Well, it should say like accuracy, use some of those terms for the metrics that we discussed. Yeah. So this could actually be viewed a little bit as overclaiming. Improves performance on all image processing by 14%. Probably not true. I totally made these numbers up. I guess it's true. Oh, yeah. So I guess you'd probably look at some recent papers at some point for this. Like, what would make you happy? How much do you want your algorithm to actually be able to improve stuff? Like, you are the measurement, you are the ruler that's going to say, like, what would make you feel like your research is actually making a betterment and improvement? Do you think that a 14% improvement is going to make a meaningful difference? And then you aim for that. And the whole point is like, okay, now from whatever thought process you put in at the time to say like 14% is an awesome bar, and me and myself and everyone else will see like a measured improvement from that, rather than saying like 0.8% or something like that may be meaningless. If your data set is 1,000 things, that I think means it classifies one more image correctly. Not huge. Maybe this is like 1 million images that are more correct, something like that. Okay, C. All right. A series of complicated experiments to support B. Is that a claim? Right hand if you think that's a strong claim that you can make. Okay, how about left hand for mm, not claim? All right, we've split the group. So then why does this sound like a claim? Better claim than B? Okay. Yeah. Maybe one way to think about this is if you're in a court of law, a claim is like the decision at the end. And then, but the experiments here is like what the lawyer is paid to do is gather evidence to eventually support the claim. So here, I wouldn't really think of C as a claim. In fact, C is because again, it's not something you're really saying. Like you're not saying A is better than B. You're saying, okay, we've definitely got some good information, hopefully, but you're still doing this for B. Yeah, that's one way of thinking about it. Well, I mean, there's going to be some theory papers that probably don't do experiments, but yeah, basically every ML paper should have some experiments in it. I mean, even a theory paper, I should say, should have at least some thought experiment or something. Okay. I was going to take others, but I think we're getting near the end of time, and I think there's supposed to be another group in here at 4, so I don't want to go too much over for any other questions. But basically, normally, claims kind of take this form. A is greater than B. In some way, some quantity is evaluated in there. There's usually some statistics rather than just greater than B, like, we're 95% confident that A is greater than B over all the data sets that we trained over. So at least we have some statistical quantity we can discuss rather than just say better, which is really hard to prove unless you're literally doing like a propositional proof. Yeah. Mm. I don't think we can come up with experiments for A, because like A is not a claim either. A was a description of the method. So an ablation is another experiment, so it's not a claim. But if you want to make a claim, yeah, that the representation and only the representation was the thing that provided the benefits for B, then you can do an ablation to support that claim. So you're saying that, but you're still saying like my algorithm is the thing that provides this benefit, but you can kind of split B into two different things. There was an improvement, and it's usually a really good evidence in a paper to say like that improvement was only because of what I did, nothing else. And that's really helpful because I find a lot of papers are still like, look, my numbers went up more than yours or something like that. And we're supposed to be doing science, which means that we collect a bunch of data and we produce facts and rules that we can reuse elsewhere. So I want to know why that number went up, not just because you used more compute. I want to know like what representation did it learn or what about the compute or data resulted in that so I can use that knowledge somewhere else. Just throwing more money and compute at the problem is not something we can keep building on forever. At least some might believe that. Okay. Um, yeah, okay, I'll do this last part real quick. What should we optimize for paper submission? Impact? Yes, we discussed that to some extent. Easy to read? Yeah, it seems to be helping at least a little bit lately because people spend too much time burning GPUs instead of reading papers and enjoying their own thoughts. So that can often help. Other ideas. I prefer to think of the reason I do and aim for writing papers as I went through this whole process, trying to reduce the amount of time that doesn't end up being so useful. And for that, I actually aim for, I always try to get my papers accepted on the first try. This might seem weird, but it just means like you should have a good estimate for like, are these claims strong enough? Do you have enough evidence for these claims? Can you reach, hopefully, like enough evidence to support those claims by the I clear rebuttal time, something like that. And then by that, you've got that because there's a real interesting cost to like submitting a paper and not getting accepted on the first time. Because even when you like submit it the next time, reviewers might get tired of that idea. You're often not going to get different reviewers. When you resubmit it, statistically, more often, one of the reviewers is going to be the same as last time. And then if you've made like no improvements, they're just going to shit on your paper so hard that they're going to convince all the other reviewers to just not like it because they're too tired to really care anyway. So there's a really important aim to try and go for like good version of getting accepted and like always put forward really good, strong work. Take some more time if you want, it's fine. And if you're doing counterfactual work, you've got more time to make it even better. So don't worry about it too much. You're learning lots. Um, yeah, it's not easy to predict, but I don't know, it works well. I mean, from this, I usually get 65, maybe 70% of the papers that I submit are accepted on the first try. And then we can go on to other research, other stuff that we've got instead. So take some more time too. You don't need to hit every paper deadline. You're again, the job is to learn how to produce knowledge. Just get better at that and the papers will flow over time. Uh, okay, references. Me, I guess. I think I meant to put a few other things in there, but I ran out of time before making these slides. Whoops. My reviewers will complain about my lack of citations and force me to add things. Okay, other questions? Like a realistic goal? Like if someone else can't figure it out? Oh, sorry, like who is standard to do the research? Yes, like I would, I guess if you're asking about this, like if someone provides one of these proposals, I'm usually much more convinced. It's also at least a rule in my lab, like if you want to have some extra resources or for to hire interns and stuff like that to work on these projects. It doesn't happen unless there's one of these. So at least I kind of put this as a baseline. But I've also seen now that this project is done, okay, cool. We're gonna have a plan for the next 2 months. We're all on the same page. And we're just going to talk about the details about why it's not doing exactly what we want. But I find that a bit too many projects are just, we're running experiments. We did something better than another, and it's not totally clear why. But here we can see what we want the paper to look like, and we just start filling in details here. So I think actually I mean, the reason I show this too is like, okay, when you're done and you're out of here, most companies are very professional at doing research and they expect things like these. Like you're not getting funding or support or compute at even any of the research institutes unless you write a document like this and say like, this is the reason why this is going to work. This is the reason why it's going to increase the share value for the company or some BS like that. And you're not going to get anything unless you do stuff like this. People have to write grants even internally inside of research companies and Google, stuff like that. So like this is a requirement. You might as well start practicing now. If you don't do this type of stuff, you're just going to work on other people's ideas and not your own. Yeah. So other questions? Also, if you're doing any sort of startup, this is also basically what you need to do. You need to convince people to give you money or resources in some way. The best way to do it is to show a plan of what you're going to have at the end and what evidence you're going to have to support it. Okay. Yeah. Hmm. Yeah. At least so I'm trying to make that this balance would at least be like write out one of these proposal documents. That's like minimum details. You can also maybe do a bit of coding for like a day. And to be honest, these days that's a fantastic idea because you've got like such good like code completion methods. You can almost come up with solutions by the end of the day. This might take longer to actually compute stuff. And that's been like really popular and helpful. So at least start from that. And then maybe after that point, like you've got some experiment running, then you can go and look into, um, okay, maybe there's some papers I can go read now that GPUs are finally burning or whatever. Now go read some papers to see whether or not there's any good input that they can give, such that, all right, maybe you'll have a better ideas for experiments next, or like data sets that everyone seems to be using for this problem. So you've got to include one of those and which baseline to include. Yeah. But basically, just don't go read papers too quickly because people tend to pigeonhole their ideas, like even into the mathematical frameworks for those ideas. So it's going to greatly reduce like the diversity of ideas in the community. Okay, so I'll wrap this up for now. I think I'm already a teeny bit late. And yeah, I'll be doing, there's 2 more sessions for this. The next one, I may or may not record, I'll choose on it, but I want to be extra frank in the next meeting about what it's like to actually work with people. People are very interesting beings. So I may record it and I'll choose whether or not to share it afterwards, but it won't be online. So I'll maybe try to find a time everyone can make it. And the last one I'm hoping to do in the middle of the iClear rebuttal session, and it'll be on rebuttal writing, which is how to convince other people and how to be very careful about how to word things when you're sharing information. So I'm sure everyone will be interested. All right, but anyways, take care, everybody. Uh, yeah, no problem. I'm trapped in Zoom. Okay, what did I do? No, it's not that. You're not taking this room. No, if there's supposed to be something, okay. Okay.
Ah, c'est not the Samsung Attend.
Did you get one of those too?
Yes, so I wanna understand what happened, because I wanna tell them no. And I want your experience.
My experience is this was the worst experience I've had since I started being a professor.
Oh, wow.
Okay.
It has been nothing but the worst waste of my time ever. It's taken me 2 years. I should probably stop recording this. Don't cut that part out of this meeting.
Yeah, I'm sorry.
That being said, I mean, I don't know what they picked for you. Mine was a really bad example. I'll just quit all those. Okay, I should stop recording now.